In this presentation, I will give a brief overview of some recent work that Toby Fischer, Michael Milford, Girish Nair, and I have completed on intelligently curating sets of reference images for visual place recognition. In particular, I'll present a Bayesian Selective Fusion approach that we have developed to select and combine informative sets of reference images given a single query image. This approach offers some very promising results on a number of difficult benchmark visual place recognition datasets. Visual place recognition involves recognizing the location or place at which a given query image is taken by comparing it to stored reference images. A key challenge in visual place recognition is that places can appear differently in the query and available reference images. For example, the query and reference images could be captured during different seasons. They could also contain different dynamic objects, such as cars, buses, or even weather effects, such as clouds or rain. There may also be significant variations in lighting or illumination between the query and reference images. For example, the query image could be captured at night or at dusk, whilst the reference images may only capture the possible places during daytime. In order to recognize places under different visual conditions, considerable effort has been directed toward developing techniques to carefully select, curate, or generate informative reference images. Techniques like experience maps have been developed to store multiple reference images of each place based on predictions or learnings about which reference images might be most useful at query time. On the other hand, techniques involving domain translation have been explored to translate reference images into the same visual appearance conditions as query images, or vice versa. For example, night to day translation can be used to translate query images captured at night into daytime conditions so that they can be compared with reference images captured during the day. In all of these approaches, however, a key remaining question is, given a query image, which reference images contain the most useful information for place recognition? This question is particularly challenging since the best reference images will vary dynamically with factors such as time of day or change of season, and of course, with the unknown place. In extreme cases, such as indoors with flickering lights or outside during sun showers, what constitutes the best reference image could actually vary quite rapidly, on the order of seconds or milliseconds. Techniques such as experience maps and domain translation therefore don't quite address this question because they either try to predict the utility of reference images at training time rather than at query time, or as in the case of domain translation, they implicitly assume extra information about the query images, like that they are captured at night. To address this question in our work, we hypothesize that different reference images or reference sets will have different utilities for different query images, with the best reference set potentially being different for query images captured under the same visual conditions, but at different places. The utility of different reference sets will thus be inherently uncertain due to the unknown place and relationship between the query and reference images. We use this hypothesis to develop a Bayesian selective fusion approach that first selects potentially informative reference sets and then weighs and fuses their individual place recognition scores using Bayesian data fusion and a measure of uncertainty in their utility for the given query image. Our Bayesian selective fusion approach complements existing visual place recognition techniques, including sequence matching, and it is training-free and descriptor-agnostic, meaning that it can be used off the shelf with descriptors such as netflad or denseflad. I'll now provide some details of our Bayesian selective fusion approach. We first assume that a single query image taken at an unknown place X is given, where the unknown place X is one of n possible places. We also assume access to multiple sets of reference images or reference sets, each containing at most one image of each of the n possible places. The first step in our Bayesian selective fusion approach is somewhat standard and involves computing descriptor distances between the query image and each of the reference images in each of the reference sets. This gives rise to M distance vectors, where the distance vector corresponding to reference U has a first element, which is the descriptor distance between the query image and the reference image from reference set U taken at the first possible place. Likewise, the last element in this descriptor vector for reference set U is the descriptor distance between the query image and the reference image from reference set U taken at place N. In previous approaches, such as using NetVLAD, a place recognition decision could be formed by either looking for the place that achieves the minimum descriptor distance across all of the reference sets, or by looking for the place that achieves the minimum average descriptor distance, where the average is taken over all of the reference sets. In contrast to these previous approaches, in the second step of our proposed Bayesian Selective Fusion approach, we find the best reference set by identifying that which achieves the minimum descriptor distance across all places. We then select all of the reference sets with their own minimum descriptor distances within some parameter gamma % of the best reference set's minimum descriptor distance. In such a way, we select the set of possible high utility reference sets. Using these selected reference sets, we then compute our final place decision by fusing them using Bayes' rule. In particular, our final place decision corresponds to the maximum posterior probability of the place X, given the descriptor distances arranged in the vectors du from all of the selected reference sets S. Our use of Bayes' rule means that prior knowledge about the location or place, for example, that arising from a motion model or previous place matches, can be encoded through the use of the prior distribution P of X. Key to the operation of our Bayesian selective fusion approach is, however, the choice of the likelihood functions, relating the likelihood of being in place X equals I, given that we observe a descriptor distance vector from reference set U, du. These likelihoods we show in the paper reduce to ratios of the descriptor distances at the specific places I being considered. These individual place likelihoods are simple to approximate. We approximate the likelihood of being in place I, given that we see a descriptor distance dui in the ith component of du, as being proportional to the number of elements in du that are greater than the descriptor distance dui. What this corresponds to is saying that it's very likely that the place is in fact I if the descriptor distance dui is very small. Conversely, we model the likelihood of not being in place I when we observe a descriptor distance dui in the ith element of du using a Gaussian distribution with the mean and variance determined by the vector du. What this corresponds to is declaring that it's very unlikely we're in place I if the descriptor distance at place I is roughly the same as all other descriptor distances in the vector. We examined the performance of our proposed Bayesian selective fusion approach on two standard datasets, the Oxford Robot Car dataset and the Nordland Train dataset. On the Oxford Robot Car dataset, we extracted traversals under sun, night, overcast, and rainy conditions. For the Nordland Train dataset, we extracted sequences from the winter, spring, summer, and autumn traversals. In both of these datasets, if we used one traversal as a source of query images, the other three were used as reference sets. We report the performance of our proposed approach using precision and recall, and when necessary as a summary statistic, the area under the curve of the precision recall plot. In all cases, larger values correspond to better performance. We compared our approach to versions of NetVLAD and Bayesian Selective Fusion that are provided with the single reference set. We also considered a baseline fusion approach that corresponds to declaring a place decision that minimizes the total or average descriptor distance across all available reference sets. In our first experiment, we compared our approach using a single reference set, termed single reference Bayesian, against a non-probabilistic net-flat approach, also with a single reference. The aim of this experiment was to examine both the utility of our new likelihood functions, as well as the ability of different reference sets to provide different utility under different conditions. For this example or experiment, we used query images from Nordland Summer, and we examined single reference approaches using either spring, winter, or fall. As you can see on this precision recall plot, our Bayesian approach uniformly outperforms the non-probabilistic net-flat approach. Furthermore, we see that there is significant performance dependence on the choice of the reference set, with Bayesian winter performing the worst and Bayesian fall performing the best, regardless of the specific Bayesian or net-flat approach used. In our second and third experiments, we compare our proposed Bayesian selective fusion approach to other fusion approaches, including the baseline fusion approach, and single reference methods that are provided with unfair prior knowledge of the best single reference set. In the case of our second experiment, the results of which are shown on the right in the upper plot, in terms of the area under the curve metric, our proposed approach outperforms the single reference methods as well as baseline fusion on Nordland Summer, Nordland Winter, and Oxford Night. There is only a minor performance difference between our Bayesian selective fusion approach and the other approaches on Oxford Sun. Similarly, in our third experiment, with the results shown in the bottom right-hand corner of this slide, our proposed Bayesian selective fusion approach was able to outperform other potential fusion approaches, either using selection or non-probabilistic means similar to our baseline fusion approach, across Nordland Summer, Nordland Winter, Nordland Fall, and Oxford Night. On the easier traversals of Oxford Sun and Oxford Rain, our proposed approach had performance similar to the existing approaches. We also performed an experiment in which the query images were drawn randomly from either the Oxford Robot Car's sun or night traversals. We can see from the precision recall plot that our Bayesian selective fusion approach outperforms approaches that use either only the dusk traversal or the overcast traversal as reference sets, and in fact, rivals the performance of net-flat when it is provided with an unfair advantage of using the best single traversal. This demonstrates the strength of our Bayesian selective fusion approach in being able to select the most informative reference sets of images. In conclusion, we've proposed a Bayesian selective fusion approach that selects and fuses informative reference images using only the given query image. Our approach complements existing visual place recognition techniques, including sequence matching. It is training-free and descriptor-agnostic. In our experiments, we've shown that it outperforms other approaches on difficult benchmark datasets, and extra experiments in our paper show how it can be used to complement specific sequence slam and dense FLAD algorithms. There are a range of potential future research directions, including combining Bayesian selective fusion with temporal Bayesian filtering, and using insights that we've gained through our design of our reference set selection in order to predict the value of new reference images.